Okay, I've got a simple LT spice circuit where I have stacked the voltages or voltage sources. This is a precursor to superposition because I want to go through what it means and the different types of analysis you see. So my net list is stacked. It's V1 10 and I assigned it 10 volts, and V2 is 2 1 and it's an AC, and I've set it for 5 volts, and I put an R load out there just so I'd have a little current. I could leave it open loop, Spice would still do it, but I would get 0 currents of 10K. So I just put a resistor out there so I'd see some current. What we've typically done is we have typically done DC analysis. So I've got to go in and put in my 5, and there we go. Okay, so V2 is AC5, V1 is, I don't think I have 10 volts there. Let's get that in. And I'm doing that on the graphical side. Okay, so now my graphical circuit matches my net list. What we typically have done is dot op, DC operating point, or DC analysis. And if I do DC analysis on this circuit, what I get is I get a voltage at wire number 1, which is above the 10 volt supply, of 10 volts. I get a voltage at wire number 2, which is across the AC voltage of 10 volts. During class, I often ask students to measure AC voltage with a DC voltmeter, and they tell me it reads pretty close to 0. And then I ask them to read DC voltage with an AC voltmeter, and it reads pretty close to 0. So what's happening in Spice is when I do a DC operating point or DC analysis, it is ignoring the AC source. So that's why you will see a 0 or 10 volts on each side. It's just ignoring that. In superposition, we often want to ignore one source or the other. And if one of them's AC and one of them's DC, then we can just do a DC operating point, and we can do an AC analysis, and we get all our values. So that is my DC operating point. It ignores the AC. So I'm going to put dot op in my net list. Okay, now I want to do AC analysis. AC analysis is something we haven't done yet. So I want to go into here and edit my simulation command, and my AC analysis points, frequency. So I'm going to go with 1 point. And if you're ever given a frequency in my class, if you're ever not given a frequency, generally in the USA, assume it's 60 because that's the most common. So, okay. You have to choose a sweep type, linear. So a linear sweep type with 1 point between 60 hertz and 60 hertz. So if you're just doing one frequency, you can select 1 point, and your start and stop frequency is the same. This is set up to step between frequencies, so I can give it a range, and then how many steps do you want between that range, and it will do your analysis for you over multiple frequencies. Generally speaking, in earlier level classes, you only want to analyze 1 point AC. So it has built a analysis line for me. Instead of dot op, it's now dot AC space LIN for linear, 1 point between 60 and 60. So LIN for linear, space 1 for 1 point, space 60, 60 is my first frequency, space 60, 60 is my second frequency. Graphically, it nulls out the .op. It's still there if I want it. And the analysis that Spice does is the one with the dot in front of it instead of the semicolon. You can probably do that in your netlist too. So now I've got my circuit set up, and now I can simulate it, and I get AC values. And what you see is my magnitude of my voltage, or my RMS, and I have a note over here. Amplitude is equal to peak value, or magnitude. And by definition, your amplitude is your peak voltage, or VP. If I'm doing Spice analysis and I'm doing AC analysis, my amplitude can be RMS. So if I know the RMS value and I do a Spice AC analysis, my amplitude can be the RMS, because that saves me having to convert to RMS. You can use peak, but if you want RMS numbers, then you got to convert. With the AC analysis, it will do it. You don't have to. You can just put in the RMS and treat the peak like it's RMS. When you go to transient analysis, which I'm about to show you, your amplitude must be your peak. You just can't get over. Can't get by with it not being, because in transient analysis you don't get these nice results in text form. You'll actually have to plot it over time like you would see on an oscilloscope. So for transient analysis you would have it. So if I wanted to know the current through my 10K resistor, it is this current that I got, 0.005 or half a milliamp through the 10K resistor of AC, with a voltage drop of 5 volts AC across it, added to what I've got in terms of DC current. And if I want to, I can go back to the dot op and simulate it. Tells me I've got 1 milliamp flowing through that, and I've got a voltage of 10 volts. So I've got 10 volts DC with a 5 volt AC waveform riding on my 10 volts across that resistor. Pretty straightforward, about as simple as you can get for this circuit. Now I want to do the transient analysis. When I do the transient analysis, I have to go in and specifically say what my AC is. And my AC is actually a sine wave. If I wanted to do a square wave or a triangle wave, you would do it with pulse, and you have to analyze the waveform as far as delay time, rise and fall. I might do an example at some point. But I can choose the sine wave, and it asks me if I want a DC offset. My amplitude for transient needs to be my peak voltage. So 5 volts RMS works out to be about 7 volts RMS, or peak, sorry. Frequency, you got to put in your frequency. And amplitude, the T delay, theta, and the phi, that has to do with phase angles and if you want a delay to start or a pause before you start feeding a signal. Number of cycles is how many cycles you want to see. So I'm going to go with 3 cycles, because generally you want to see 3 complete cycles of a waveform. You can make it 2. You can sometimes make it 1. So that's my transient analysis. That's not my transient analysis. I have to change my V2 to be a sine function before I can do transient. And so what happens is V2 has changed on me. It's still between 2 and 1, so V2 space 2 space 1 space. But now instead of AC5, it is sine, S-I-N-E, open parentheses, 0, 7 for amplitude, 60 for frequency, The 3 we left blank are all represented by zeros and 3 cycles. So everything we typed in or we filled in the graphic mode, you can type in a text mode. You just got to know what goes where. And so the first one's DC offset. We left that 0. 7 is amplitude. That's the second. So it's sine, open parentheses, 0, space, 7. That's amplitude, space, 60. That's frequency. Generally speaking, you can ignore the next 3. So it's 0, space, 0, space, 0 for a total of 3 zeros. Space, number of cycles, 3. So that then becomes my net list. So now I'm telling Spice this is a sine wave, 60 cycles, 60 hertz sine wave. I want 3 cycles of it, and it's got a 7 volt peak waveform. Now we want to set up transient analysis. Transient analysis is pretty easy to set up. It asks for a stop time, which based on a 60 hertz cycle, which is 17 milliseconds, and we want 3 of them, 3 times 17 is 51 milliseconds, or 0.051 seconds. Our time to start saving data can be 0, which is immediate, and our maximum time per step. You generally want, this is not a true analog calculation, it's a digital one, so it basically takes a calculation at a moment in time and puts it together and makes a graph for you. So if my maximum time per step, we need about 10 data points per cycle. So if I do 10 data points in a cycle that is 0.017, then my time per step needs to have an extra 0, or 0.0017, which is pretty straightforward. And then I can click OK, and now I have a tran analysis. So my tran analysis line, I'm going to get rid of the .ac and make it .tran space 0 space 0.051, which is the total time that I want this to simulate, and or the end time, my stop time, space 0, which is my start time, and then how often do I want it to sample in time, which is 0.00017. So I'm going to sample 10 times for every cycle. So now I've got my transient analysis, I've got my DC, I've got my AC, and so now I can simulate and run it. And what happens when I run it is graphically a window opens and I can plot what I've got. So if I look at a voltage probe graphically and I look at the voltage at node 1 with respect to node 0, it's showing me my 10 volt DC source, which we would expect. If I look at the voltage on node 2 to 0, it's showing me a 7 volt peak to minus 7 volt peak AC waveform riding on a 10 volt bias. So I'm actually combining an AC source and a DC source. And what a DC offset does is it just shifts to 0. Instead of this going between plus 7 and minus 7, it now goes between 17 and minus 17. And if I want to see the current, it's going to show you the current. If I hover over the resistor and I click, it shows me the current. And it shows me that my milliamps is following my voltage. And my milliamp scale popped up on the right side of my scope, if you will. And the voltage is over here on the left for the y-axis. My x-axis is always time, just like on an oscilloscope. So those are the 3 analyses that you will use the most. We will use .op for most of the DC circuits. When we get into some AC circuits and we're only on AC, we'll probably do the AC analysis at a certain frequency. If we get a mixed signal like a superposition problem, then we either have to do multiple AC analysis, track answers, and add them, or you could look at it all in one as a transient analysis. But either way works. And that, if you can duplicate this, you will be in good shape. Have a great day.